You've probably all heard the stories and read some studies about impact of performance on user experience. And so you probably heard the headlines like a 1 second delay in load time leads to a 7% drop in conversion and 11% lower page views. We have all heard these. We also heard that 1 in 4 people will abandon a page that takes longer than 4 seconds to load, and 74% of mobile users give up if a page takes 5 seconds or more to load. We've also heard the stories about the fact that 1 second delay in page load will decrease customer satisfaction by about 16%. And 79% of users who are dissatisfied with a website's performance are less likely to buy from the same site again. But that's not even the whole story. The worst part is that 44% of those users will tell their friends about the bad experience online. So you probably shouldn't expect many new customers if you are known for bad user experience. But there is another interesting dimension that we frequently forget about when we look at performance, and that's the carbon footprint. And in an interesting study that researchers at the University of Massachusetts Amherst performed, so they've realized that some of the neural networks that are used in production right now can generate 626,000 pounds of carbon dioxide equivalent, which is nearly 5 times the lifetime emissions of an average American car, and that includes manufacture of the car itself. So that's crazy stuff. And there is also another interesting study from AI and compute that was released recently, and it analyzed the impact of the largest AI training runs, and turns out that we are actually growing exponentially. So improvements in compute have been a key component of AI progress. So long as this trend continues, it's worth preparing for the implications of systems far outside today's capabilities. So we should definitely start thinking about these trends as well. And I strongly believe that all of us have an opportunity and obligation to improve experience of our users and reduce carbon footprint. So hello and welcome to Performance 4. My name is Taras, and I am super excited and honored to welcome all of you to our 4th Performance Summit, where we'll hopefully share and learn some of the latest ideas and approaches for improving software performance. Since we have a pretty busy agenda, I'll just give the word to our legend of performance optimizations, Rico, who's gonna talk about his war stories, and it's always exciting.
Good morning and welcome. I'm honored to be here for the second time, and I have a couple of fun stories for you this morning. This is once again, this is just like a really this is a super fun thing for me to get to do. Come and tell a couple stories and maybe kick off the day and get people's juices flowing. These particular stories are extra fun because they have sort of that Sherlock Holmes moment where you're kind of staring at the data and trying to figure out what it means, and the answer is actually kind of in front of you, but it's not necessarily obvious. And then when you have that eureka moment, the actual thing that you need to do is very, very simple, and you can sound super impressive to your friends for coming up with this little conclusion. So let me just jump into these. There's 2 different ones. Both of them are from my time working on Sidewalk.com. I thought it would be fun to talk about an online property a little bit. Let me say a few words about Sidewalk.com before I start. The effort started like around 1995, little after, right on Windows 95 launch day, actually, was when I was hired for it, and I was the first dev hire. And there were multiple launches of different versions over the next couple of years. And it was a very interesting property because it was one of the only properties of its era that actually had completely computed data. All the pages were, computed pages. At the time, it was much more common to have either straight HTML or HTML that had been sort of produced by some kind of a printing press program the night before or on an hourly schedule or something like that. But users were always getting straight HTML. And we didn't do that. We had highly personalized content, based on what device you had and what your preferences were and so forth. So no one saw the same page twice, and that was pretty new. So here, let me just jump into it. So yeah, we had all computed content, and we were doing, at this point, we could do about 30 requests per second, and we needed something like 25-ish in order to carry our expected load. And we were able to do 30, but it didn't last. Like, what was going on was over the, we would start at 30, it would run fine at about 30, 30, 30, 30. And then it would start to erode, and it would erode and erode and erode. And over the course of 15 minutes or so, it would become stable at more like 10 requests per second, which was considerably slower than we could afford to be. And we only had 2 weeks before launch at this point. So we were kind of in a panic. This was an all hands on deck kind of situation. I remember putting flipboards into the hallways, where people could just write ideas for what might be going on and what they thought we should investigate, or to communicate what they were working on. And, you could put your initials by an idea to sort of indicate that, you were working on that idea. And it's kind of funny, going back to like 1994, our idea of team communication was to have sufficiently many flipboard charts in the hallways that like anyone could see what was going on. And it worked. I mean, we were a team of 20, but anyway, okay. So the situation was this. Based on the data. The tests were set up so that the load would be sufficient to keep the CPU maxed out. Okay, so it would keep adding load and adding load and adding load. So naturally, CPU was flat. Okay, but of course, requests per second were going down. And interestingly, I/O was also going down. So like you might think, oh, well, maybe the database is getting clogged, or maybe there's some, wonky disk thing, or what, but no, I/O was going down. So the I/O seemed to be proportional to the requests. And so as the request went down, the I/O went down. And an interesting thing we noticed was that throughout all of this, page faults per second remained constant. And we kind of expected, page faults per second would, maybe be increasing if load was powered, but actually it turns out to be sort of this universal constant of web servers. Like, in many ways, they were capped by how much faulting they could possibly do, And so, okay, if faults per second is constant, then this leads you to sort of this inescapable conclusion that faults per request must be increasing. And actually, this colored the way we thought about page rendering from then forward, because we were always thinking, okay, what could we be doing to keep faults low? And then all of that is about driving locality, churning the heap less, and so forth, all those kinds of things. But okay, with this data, faults per request is increasing. So what the heck is going on? We understood the memory hierarchy well enough. And so, I have this little representative picture here to indicate what decreases. But of course, we knew all that. So what's going on here? Well, okay. So with disk I/O going down, it's not hard faults, right? If it was hard faults, we'd see a long disk queue and stuff, but nope, we're not seeing a long disk queue. We're seeing disk activity going down. So, okay, so it's soft faults. Okay, well, what kind of soft faults? We could get soft faults from a variety of sources. Maybe we were, bringing code back in or not, but like the program was actually not that big. So it was not very hard to see that we were talking about demand zero faults. Okay, so that's us asking for new memory. Great. Okay, so a little bit more looking, VM use is actually growing. So virtual memory is going up. So the next thing you think is, oh, there must be leaks. Okay, so we look for leaks, but actually we found leaks. Interestingly, by starting and very carefully looking for leaks and putting in instrumentation so that we could discover the leaks, we discovered that there were some, but there were not anywhere near enough leaks to explain what was going on. And by the time we had fixed a couple of these comparatively minor leaks, it was very clear heap allocated size was constant. So that's when the real light bulb went off. If the heap size is constant, but the VM size is growing, there must be fragmentation. And the fragmentation would tend to increase, would tend to explain two things. First, poor locality. So of course that would drive requests per second down, but also the heap was continuing to grow because fragmentation, so we would continue to see demand zero faults until finally, it stabilized at some equilibrium point where, there was enough space that it just didn't need to grow very much more, and things were kind of, being freed enough in the different fragments. But the heap had grown to a much bigger size by then, and, by then, like, everything was kind of crazy nuts. And interestingly, at the stable point, the system was giving back memory to the OS and then demanding it back because, space was becoming freed because of these sort of these leftover pieces in the fragmented heap. And so when one of these would go away, a chunk of memory could go back to the OS. But of course, the very next thing we would do is ask for it again. And so boom, another demand zero fault. And so the whole thing, kind of stays in this horrible kind of place. So actually, the solution to this was very straightforward. Once we realized that the heap was fragmenting, we used this dual heap solution to kind of get things more stable. So we already had a situation where every thread had its own heap, okay? And here I'm calling it the A heap, and we'll talk about the B heap in a minute, okay? So there was one affinitized heap per thread. Okay, and we did that so there would be no need for locking, right? So almost all the allocations that any thread ever did was on its own private heap, and only comparatively few objects had to be allocated on some kind of shared heap. I didn't even show the shared heap in this diagram. Okay, so we already had that. So what we did was we added a second heap per thread, okay? And we would begin by just allocating everything out of the A heap. And the B heap would be pristine and empty and so forth. And when we got to 1 million allocs, we would just switch heaps and now start allocating out of the B heap. And what's interesting here is that all the new allocations are happening out of the B heap. And so the A heap is getting nothing but frees, right? Free. Anything that's, been around for any amount of time, whatever, any kind of objects, any kind of whatever is going to get freed. So over the course of a few million allocations, well, actually, we just did the switch point at 1 million allocations. By the time we got to the 1 million allocation point, the A heap was empty, okay? It was, again, pristine. And the B heap was just starting to get loaded and fragmented enough to start exhibiting problems maybe, and then we'd switch again. So now the B heap gets only frees and all the allocs go to A. Of course, allocs and frees are going to A. A is being used normally, but B is no longer taking any alloc load. So B is getting strictly cleaned up, right? And so now B is cleaned up, run on A for 1 million allocs, and then boom, switch back to B. And so you're always, every million allocs, you're switching to a completely pristine heap. Now, interestingly, at the time, the Windows heap was actually quite poor, and because this is like circa 1996, right? Windows added a thing called the low fragmentation heap years later to kind of avoid this whole class of problem, because people were doing wonky things with private heaps and whatnot, and it made it harder to share memory and all sorts of things. So, but this particular solution was very, very simple, and interestingly, like, of course, overall virtual memory was lower with this strategy because of the lack of fragmentation. So VM allocs would be less, and the working set was comparable, because although there were two heaps potentially live at any given moment, most of one heap wasn't in use. So the average working set actually was no different than with just one heap before any fragmentation was going on. So actually the marginal cost of this was very, very low, and we were quite successful. And it's interesting because when we got, to actually doing the fix, it was like a 5-minute fix to just bolt on a second heap and, do this back and forth thing. And so we went from, oh no, what are we going to do, to, oh yeah, here's 20 lines of code and a 5-minute diff, and away you go, and we had landed. So pretty happy, satisfactory solution here, and good illustration of heap stuff. Okay, the second one, I have a summary slide. Yeah, so the result, we stayed flat at 30 requests per second, and we didn't see observed requests going up, and the 1 million number was picked based on allocation rate. So yeah, good. Okay. The second problem, this was a little bit later in Sidewalks history, where we were working on Yellow Pages, and here we got this very interesting problem. It was like the day after we launched. Okay. And I was in the office with my operations lead, Eric, and he was telling me that we were seeing this bad problem, and we'd seen it as soon as we started getting any kind of significant load. And it tended to happen only during the times of day where we were fairly busy. Overnight it had been fine when we had deployed, but it was bad that morning and seemed to be getting worse, and it was occurring when we were under load. And so basically what was happening was, about once every 10 minutes we'd see this huge backlog, and he was easily able to demonstrate it. He's like, just run a little query, any little thing, and you'll see, just hit refresh, and it's working, and then it would just kind of have this giant seizure, and then in about 45 seconds or so it would come back, and then it would be fine for another 10 minutes. And we're like, what the heck is going on? Okay, all right, so what is the data telling us? Well, we saw from our logs that during the hiccups the server was working on what we called a hard query. Okay, and the hard queries, they were hard. They could take about 45 seconds to finish, because you can ask fairly tricky questions of the Yellow Pages thing involving lots of physical reads. By contrast, easy queries were more like 200 milliseconds, right? So, and more, queries tended to be much more like the easy queries than the hard queries. But we didn't want to stop people from doing this stuff, and we expected that they would be infrequent enough that they really wouldn't cause a big disruption of service. And if you wanted the answer, you wanted the answer. Now, interestingly, one of the things that happens here is, if you get a slow query that's like 45 seconds or something, you do the worst possible thing, which is like hit refresh and thereby reissue the query. So now there's 2 of them in the queue. So later we actually added additional mitigation. So if we started getting behind, we would stop working on things, and we would take things off of the front of the queue, so that people were less likely to hit refresh on the slow moving stuff. But anyway, okay, 45 seconds to finish this query. Crazy, right? Okay, so I'm thinking 45 seconds, like, all right, and like, so we're going to have some number of these queries coming in, and some of them are going to take a long time, and then I'm thinking, is this even abnormal? Like, what's the deal on this? What should I reasonably expect? And so I started thinking, okay, what if I think about the arrival of a bad query, a hard query, as being a random independent event? Okay, we just happen to get one, and I'm like, okay, well, that sounds like a Poisson process. Okay, and I have this lovely Poisson chart here, and we'll see some Excel on this in just a second. Okay, so a Poisson process. Okay, so if it's a Poisson process, how many of these could I reasonably expect, right? All I need to know to get that answer is the average number of queries in a typical minute, the average number of hard queries in a typical minute. And we had that. We could look at the log and we could see 5.5 hard queries per minute. Okay, great. So let's go to the chart. Excel, lucky for us, speaks Poisson. So I made this little spreadsheet up that had the sort of cumulative probability of a particular thing happening. And so if you look at the rows, each row corresponds to a particular frequency of the bad event. And it doesn't really matter what it is. Of course, the Poisson math doesn't care, right? And so the row of interest is 5.5. And then the columns are the probability that you'll have greater than or equal to that amount of hard ones in any given minute. Okay, so obviously 100% chance that there's greater than or equal to 0, and then it falls off, as you can see. And the cell that's of greatest interest is, of course, that 10.6%, right at 5.5 and greater than or equal to 9. Okay, and let me explain to you why that cell is so important. And so hold that number in your head, and also look at that green number, 0.2% at 14. Okay, those are going to be the interesting numbers. That number, 10.6%, means that there is a 10.6% chance of having 9 or more hard queries in a given minute. So why do I care? Well, the reason I care is that I know another number. I had done the scalability testing with my colleagues, okay, and it had showed that the maximum net throughput for the system happened at 9 threads. So that's how we had configured things, right? Keeping in mind, this is like, 1997-ish now era hardware, okay? So this is not some 64-core processor with like gigabytes and gigabytes of memory. This was like a 256 box machine with 8 processors, I think. So 9 threads turned out to be the optimal. Great. If all 9 of them are doing something hard, anything new that comes along is going to have to be waiting behind at least one hard problem, right? Yeah, so ouch. And how likely is that to happen in any given minute? Well, it says right there, right? 10.6% of minutes will have this problem, so about 1 in 10. Yeah, so double ouch. But I knew another number. Okay, I knew that the testing had shown that the fall off from 9 threads in terms of overall throughput was gentle, which is to say 10 isn't much worse than 9. Okay, in fact, it didn't really start off falling off really particularly badly until you got, well into the teens. Okay, so what we knew was that increasing all the way up to even 14 threads would only cause maybe a 15% degradation in total throughput because of the additional contention. And recall, the magic number, okay, at 14 threads is 0.2%. So instead of 10% of our minutes having this problem, only 0.2% of minutes would have this problem. Now, 0.2% of minutes, that means that even during the whole period when the system is under its highest load, the likelihood is we wouldn't even get one such event before the load went away. So that's great. So all we did was tweak our registry because the total number of threads was completely configurable. So it's kind of a magic moment, right? I'm in there with Eric, right? And we're like, hey, is Carl down in the, and it was Carl, right? Okay, so not that any of you guys know Carl, but like, is Carl down at the center now? And he's like, yeah, Carl's at the data center. I'm like, call him up and tell him to change this entry in the registry from 9 to 14. And don't tell him why. And so Eric's like, okay, because I've been working with him. So he calls up Carl and he says, do this thing, right? And and we push the button on the load thing, and boom, like instantly, all the hiccups were gone. And this is such a great little example, because what had happened here was we had traded overall throughput, because we were going to be serving a little bit less, 15% less, but we could afford that. But the overall experience was much more smooth, right? So additional threads, creating that additional capacity so that even if there are quite a few, hard problems running at the moment, we can still be handling the more typical load with what's left. And then, most of the time we have plenty of time to catch up. So there's lots more elasticity in the system, and hence nice, smoother delivery. And users just absolutely love that. Much, much better. So anyway, that's my 2 stories. So I hope you'll find that a little bit entertaining and motivational for the rest of the day. Again, it was my pleasure being here for you today, and enjoy the rest of the conference. And I think there's time for questions now, so we'll take a couple of questions. Thank you so much.
Awesome. Thank you so much, Rico. It was, as always, very inspiring and informational. Forward for the questions. I'd like to remind all the attendees that they are welcome to type their questions in the corresponding Slack channel that is created for each of the talks. And since there are currently no... Oh, so looks like Robert has a question.
Robert,
He's wondering.
asking me about queuing theory. Actually, I have a funny story there. I ended up studying queuing theory on accident. How do you accidentally study queuing theory? I wasn't planning on taking queuing theory. I had planned to take this course on communications, which was going to be super easy because my senior year was going to be brutal. And then they canceled the communications course at the last minute because not enough people signed up. And I had to take something off the list of requirements to graduate. And one of them was queuing theory, and I had none of the prerequisites. And so I got myself signed into a queuing theory class, and I was like, oh God, I don't even know. And like, just take the class, it'll be fine. Here's some books. So I ended up learning queuing theory in my senior year. And yeah, part of the reason that I reached for the Poisson process right away was I had some grounding in queuing theory. And I often use queuing theory to predict what load looks like and what wait times look like. In fact, one of the things I like to talk about is like anytime you put a lock around anything, congratulations, you've made a software resource. And a software resource exhibits many of the same kinds of issues as hardware resources, which is to say there's going to be a queue in front of it. It could convoy. It has a service time. You could model the wait time, and if you have some idea what the distribution of service times looks like, then you can use a queuing model to get a sense of it. In this particular case, queuing theory, I didn't reach for it because we didn't have a very good idea what the distribution of the incoming queries was overall. But we did have a sense that there were sort of normalish ones, punctuated by these really just horrible, horrible things that could be taking like 45 minutes. And they were just way out there. But they were happening often enough, an average of 5.5 of them per minute, right? That they caused a measurable impact on the system. So but yeah, I love this stuff, and in fact, we absolutely could have caught this if we'd thought about doing a Monte Carlo simulation to do this kind of thing. And I've done that in other cases for network traffic. I even did one for a pipeline to a graphics card to get a sense of like how many frames are going, what's the arrival rate of frames on drawing, what's the bandwidth look like, and how are we going to queue up on the GPU. And it's only approximately correct, but it's pretty good for doing in a few minutes. You can do an on paper kind of thing. I don't always use the simplest queuing model, but one that works pretty good, I can't remember the name now, is where there's two distributions. There's a probability that it's the easy distribution and a probability that it's the hard distribution, if you will. And you can model that analytically and get a decent solution, and that works pretty well. And that one often is quite serviceable, and it has a closed form solution. And if I remember the name, but anyway, you can look it up. It's pretty well understood. The paper on it is only about 2 pages long, and anyone with any grounding, in algebra can do it. And you could do queuing theory. Someday I should do a talk on using queuing theory. But yeah, love that stuff, which I accidentally learned. I was minding my own business when suddenly I was learning queuing theory. Anyway, I'll be watching the Slack the whole rest of the time too. So if you think of questions later, I'm happy to answer them. Is there anything else, or I could move on?
Thank you, Rico.
Actually, we have like yield.
Yeah. Well, so since we kind of don't have any more questions, I have one quick question. If you could go back into the past and give yourself an advice, like a single advice for your career or performance investigations, like what would it be?
Oh man, like one thing. The thing I tell everybody, I think, my top line advice is plan on being wrong a lot. Okay. So, whatever you do, don't get too married to any one theory. And I think back in those days, I would spend a lot of time evaluating losers. And so these days, I'm much more skeptical of my own ideas, and I try to come up with cheesy ways to refute my own ideas or to confirm that I'm on the right track. Like it's all fine. And, here I talked about in these slides, like 2, sort of victories, right? But like like I didn't mention the other week where we tried piles of other stuff, none of which worked, right? Like, so, this sort of miraculous solution, like, well, of course, that's the miracle because, in hindsight, I'm only showing you what the winner was, but we wasted a lot of time on bad ideas. And so I think the most important thing to do is remember that you're wrong. And I think if I could pick one other thing, it would be that I tell people not to use time so much for measurements. And in both of these cases, it's essential to be thinking about resource consumption to get to the truth. And so another sort of top line advice I have for everybody is stop thinking about time, because time is rarely diagnostic, and think about consumption. With time, I like to say time is data I can only cry about. So getting to the crux of what resources are churning, and maybe they're software resources, is generally pretty probative. And so I kind of wish I'd learned those tricks earlier in my career. But I mean, like I was still a greenhorn. Everyone has a greenhorn, and you just kind of, you got to learn sometime. And usually you learn by making a lot of mistakes.
Well, I don't think you do, but it's definitely very inspiring. There is another question. By the way, a reminder that please ask your questions in the dedicated channel for the talk, not on the general Perf Summit 4 channel. So the question is, what's the end of the story? What have happened after you've changed threads to 14?
Yeah, it was pretty smooth. It was exactly as expected. We took a modest throughput hit. We had modeled that in the lab before because we did scaling tests to see, at which thread level did we get the highest throughput, and the magic number was 9. But 10 was only like 2% slower, and 11 was maybe 1% slower than that. And if you went all the way up to 14, we only took a 15% hit in performance. And then after that, we never got the hiccups because the probability of getting a bad minute went to 0.2%. Well, at 0.2%, the load didn't last long enough that we were substantially likely to get a hiccup at all during the load period. So maybe we might get a hiccup once a month or so because we might, get unfortunate, 0.2% of the minutes, but typically we just didn't see it. So we took an overall throughput hit of 15%, which we could afford to get smooth delivery and avoid the hiccups. So yeah, it was pretty good overall, and it was like one number. So it was kind of fun because we diagnosed that one pretty quickly. I was literally walking down to see Eric to ask him how it was going, and he's like, "This weird thing is happening." And 45 minutes later, and some Excel spreadsheets and a chalkboard, right? We had the answer, and we didn't even have to take additional measurements on that because we had, just from the logs and the available telemetry we had, everything we needed was there. The key observation was that what was happening wasn't even abnormal, and so we needed to account for it, and we hadn't thought about it. And none of our models had anything like 45-second queries. All our test cases were way cheaper than that. So another thing we learned was we were doing a lousy job of simulating the diversity of queries that our customers were going to produce. So we started using the logs to do performance testing, where we would take actual queries that had run over the course of a week and replay them, rather than the synthetic stuff we've been producing, which had been too homogeneous. So there you go. Another part of the story.
Cool. Thank you so much, Rico, again.